Welcome to 3.5 related rates part 2, where we're going to look into just some of those other kind of classic problems that are involved. And this is a pretty typical one, kind of a filling of a tank. Certainly these can be quite easy if the three-dimensional prism has a regular area that's produced over the height. These become kind of a joke because it's a constant rate of change. But this particular case is an inverted cone, where water is being kind of dumped in at a rate of 1.5 cubic meters per minute. Ooh, sorry about that. So similar to the other one, as we go and we identify some of these kind of calculus quantities, it's a really good idea to write them down as you go. So if water is being pumped into the tank at a rate of 1.6, that is the rate of change of volume with respect to time. And I'm going to put that's 1.6 cubic meters per minute. Now, I think immediately, if we're going to talk about volume, it's nice to think about that formula for volume. In the case of a cone, the volume of a cone is 1/3 pi r squared times the height. And immediately there's a bit of a problem there because that's a three-variable equation. There's volume, radius, and height, and none of them are constant. As that water fills this tank, and I'll use this diagram over here, the overall triangle is that the cone itself has a radius of 3 because the diameter is 6. So I'll write that down, sorry. If diameter is 6, then radius is 3. And we know that it would also have an overall height, or a total height, of 5 meters. Now, I'm going to draw this other triangle within the same one that at some point, so some general point along the way, this will be the radius of the water and the height of the water. Maybe should have used blue there for water, but that's okay. Now, this brings home a concept that most students haven't thought about since Math 9, I believe, which is the concept of similar triangles. And there's two triangles here. There's the 3, 4, or the 3, 5, and actually the diagonal doesn't matter. The hypotenuse doesn't matter. And then it's the RH. And you haven't talked about similar triangles in a while, but the concept that's pretty crucial with similar triangles is that the ratio of sides is maintained. And what we can do in this case then is we can say that R over H in the small red triangle is equal to the radius of 3 over the height of 5 in the large triangle. And the reason why that's so important is because this question, all it wants is dH over dt when the height of the water is 2. We don't care about the radius, which means if we can somehow manipulate our volume formula to be only in terms of volume and radius, then we can do our implicit differentiation and solve from there. And the way that we do that is by isolating R in this particular formula. And that is that R is equal to 3/5 times the height. Now, what we're going to do here is we're going to take our volume formula and the expression that relates radius to height, and we're going to combine them. And now what I'm going to have is that volume is equal to 1/3 times pi times 3 over 5h squared instead of r squared, and then that remaining h at the back end as well. Now, certainly there's a little bit of cleanup that can be done there. If I'm going to multiply 1/3 pi by 3/5 h squared, I'll write out that intermediate step, that this is 1/3 times pi times 9 over 25 h squared, and then that other h, or additional h factor, is on the end. We'll clean this up as much as possible. So I get that volume is a function of height, and that's why function notation is so nice, that really what this is at this point is the volume as a function of the height of the water. And in this case, we will multiply all the numerators, so I will have 9 pi over 75 h cubed. Definitely a bit of an odd kind of formula there, but really important that the advantage now is that we are able to simplify and work with this and basically relate dV over dt to dH over dt. And the way that we do that is by introducing our derivative. So d over dt of V is equal to d over dt. A little bit of a kind of a gnarly formula here for sure. We have 9 pi over 75 h cubed. When I take the derivative of the left-hand side, this does just become dV over dt, nice and clean and easy. The right-hand side, though, is the 3, the exponent, will multiply onto the coefficient. So I'm going to write that as 27 pi over 75. Now the power has been reduced by 1, so it's h squared. But again, implicit differentiation. We have to include dH over dt. It is totally up to you if you want to manipulate at this point or after you put numbers in. I am pretty indifferent as to which way you do it because most of these questions ultimately boil down to some kind of a manipulation. I do like manipulating for it first. So I'm going to quickly write that dH over dt is equal to, and I'll write this as 75 times dV over dt divided by 27 pi h squared. So the last thing is to put in the info that we know, and I'm going to say that dH over dt, when the height is equal to 2, is equal to 75 times the volume entering the cone is actually constant. So think just, a hose with constant flow coming out of it. But at this particular point in time, H is 2. Now, we are certainly going to, use our calculator for this. There's nothing wrong with this. And I'm going to do a little bit of a shortcut here. This would certainly clean up into 10 over 9 pi. But we are going to leave that as 0.4, right? Just round it to the nearest tenth. Now, units. The volume was measured in cubic meters, so the height is measured in meters. The time at which that volume was being chugged into the tank was in minutes or meters cubed per minute, so the rate of change of my height is 0.4 meters per minute. All right, definitely a bit trickier if you compare that to, the first example. Similar triangles do come up a fair amount, so we have to be really comfortable with that concept, and we will see it more than once. In fact, we see it immediately after in this third example. A spotlight shines on the ground on a wall, a spotlight on the ground shines on a wall 10 meters away. A man or person, 2 meters tall walks from the spotlight towards the wall at a speed of 1.2 meters per second. How fast is the shadow on the wall decreasing when he is 3 meters from the wall? Definitely a lot of stuff happening in this question. And like most of these related rate questions, it's important to draw a diagram. So that right there is going to be my spotlight. And then due to my lack of artistic skills, the stickman is going to be our person. And then as that light is shone from the spotlight, what's going to happen is it's going to cast a shadow on the wall at the far end. Now, we know that the wall is 10 meters away. We don't know how tall the wall is, and that is okay. What we're going to do instead is we're going to identify the y variable, and I'll write it in here, as the shadow on the wall. And then what we're going to do is, and it doesn't really matter where you put it, but I am going to say that this person is X meters away from the spotlight. And what that means is that the remaining distance to the wall is going to be the total of 10 meters minus the distance they are away from the spotlight, which is 10 minus X. Now, what this does for us is it does create two triangles. It can be a little bit difficult to see, so I'm going to draw this kind of inner triangle, if we want to, as red. And we know that the height of the person is 2. And the reason why that's such a big advantage is because that ultimately allows us to relate these variables to each other. And if you picture what's happening in this question, it's that the man is walking away from the spotlight at a speed of 1.2 meters per second. So we have two changing quantities here. We have dx over dt, which is the rate of change of the distance of the person to the spotlight, and that is changing or increasing at 1.2 meters per second. What we are trying to determine is what is dy over dt. That's the rate at which the shadow is increasing. Now, it is nice when they do this for us. It says that how fast is the shadow of the wall decreasing when he is 3 meters from the wall. Now, that gives us the initial, or what we often call initial conditions, which is the idea that that is the particular point in time when we're trying to find out how fast the shadow is decreasing. Now, because the shadow is decreasing, that does let me know that dy over dt should be less than 0. Right? Decreasing indicates a negative rate of change. Now, I always like drawing a bit of a diagram for kind of what's going to happen at that point. And when he is 3 meters from the wall, if we look at this diagram, he's still 2 meters tall, so it's going to be a little bit out of scale. But if he is 3 meters from the wall, then he's 7 meters away from the spotlight. He is still 2 meters tall, and that's going to give us some pretty important information about how we can determine y and kind of go from there. Now, the best way of doing this question by far is because we are trying to find dy over dt, I am going to rearrange using special triangles and get an equation that relates y in terms of x. And the way that we do that is with the diagram above, and I'll just draw an arrow so we understand where I'm talking from. And I'm going to take the dimensions of the large triangle, which has a height of y and a base of 10. It starts, the spotlight is 10 meters from the wall. And that's going to be equal to what we want to call maybe the inner triangle, which is the height of the person over the distance they are from the spotlight. Now, your best bet here is to now manipulate y in terms of x. I'm not going to call it cross multiplication. What I am going to say is that we are multiplying the entire equation by 10, and that will distribute onto both sides. And I get that y is equal to 20 over x, or as I'm sure you're used to at this point, it is a little bit friendlier in calculus to write that as a negative exponent. And if y is equal to 20 times x to the negative 1, when I take the derivative with respect to time of both sides, what I end up with is dy over dt, which is the rate at which the shadow is decreasing, is equal to the derivative of this is negative 20 times x to the negative 2. But we didn't take the derivative with respect to x, we took it with respect to t, so we need to make sure that Leibniz fraction shows up one more time. The last part then is we want to know dy over dt when he is 7 meters away from the wall. When he is 7 meters away from the wall, or sorry, 3 meters away from the wall, x is 7. And we established that above. I'm just going to scroll a little bit. I know that's a little bit annoying. That basically this 7 is x. So we are finding dy over dt when x is 7. And it's a little bit unique in that dy over dt, this expression right here, only depends on x. So certainly we could find out how large or how long the shadow is on the wall when he's 3 meters away from the wall, but we don't need to, because we are going to be evaluating dy over dt when x is equal to 7. So all I'm going to do is replace that x with 7. And remember above, we identified that dx over dt, or we were given that it was 1.2. Just kind of separate that a little bit. And what we end up with is that dy over dt, and there's our negative right there. I'll write this out. This is negative 20 times 1.2 divided by 7 squared. And I kept that as a fraction just because it does work so nice and cleanly, but it's negative 24 over 49. So right around, negative 0.5 meters per second. And we do see that we got a negative quantity, which makes sense because the closer he is to the wall, the smaller that shadow is. And it's worth mentioning that if he stands against the wall, he's casting a shadow that is 2 meters high, which would be the minimum height of the shadow. Not asked for in the question, but always important, I think, to think about that. Okay, last one here, and this is probably the most typical question, and a really good use of this. It's really what I like to call kind of the distance between objects. So it says that a man starts walking north at a speed of 1.5, and a woman starts at the same point walking west at a speed of 2. Almost feels like a physics question. Always good that they generally tell us. I just got to make sure I get well, if he's going north, that won't quite be enough room. So I am going to put point P right here. And then what we're going to have is that the man is walking to the north, and I'm going to call that x as he, maybe I should call that, well, we'll keep it as x, it doesn't matter. A variable is a variable, it will make no difference. And then the woman is walking to the west at a speed of 2, but we'll identify that as y. Now, it does say at what rate is the distance between the man and the woman increasing? That would be this dimension right here. And as much as it does suck, I am going to call that z. Now, if the man is walking north and the woman is walking west, there is a 90-degree angle between them, and that is massively important because that's how we relate these variables. I can now say, and I like to write the relation right away, that according to Pythagoras, in this case and how I've defined these variables, z squared is equal to x squared plus y squared. Now, it wants to know at what rate the distance between the man and the woman is increasing. That is dz over dt. That is our unknown. And logically, if you think kind of that math with intent, that as we go through this question, we are going to end up talking about dx over dt and dy over dt. Now it tells us that the man is walking at a speed of 1.5 meters per second. So dx over dt is 1.5 meters per second. Kind of a weird 5 there. I'll try to fix that. Whereas the woman is walking to the west at a speed of 2. So this is going to be 2 meters per second. Both of those are increasing. From those pieces of information, what we can do is we can basically take the derivative. Now, when I do take the derivative with respect to time on both sides, I get 2 times z times dz over dt is equal to 2 times x times dx over dt. I'm just going to run out of room. I have to move that down. And then I would also have plus 2y times dy over dt. Now, unlike the previous question, this does have z, x, and y within. So what we need to know is the values of z, x, and y 1 minute later. Now, this is typically not a problem for students because what I usually encourage them to do is kind of underneath their diagram, say at 1 minute, and then draw what that triangle would look like. Now, if they are walking for 1 minute at a speed of 1.5 meters per second, there are 60 seconds in a minute, and I'm going to multiply that by 1.5 meters per second. This is why I spend so much time on unit analysis in physics or Math 20, because ultimately, if you know how the units behave or interact with each other, it's a good guideline as to what you have to do. So in 1 minute, the man has walked 90 meters, And in 1 minute, the woman has walked 120 meters. Just to write that again, that is 60 seconds. The woman is walking at 2 meters per second. The seconds cancel. 60 times 1.5 was 90, and 60 times 2 was 120. The problem is that we're not given any information about Z, but we initially set up a question, or sorry, an equation, and we said that Z squared was equal to X squared plus Y squared. Now, Z, X, and Y in this context are distances. So although certainly mathematically we would typically write the positive and negative root of X squared plus Y squared, we do not need to worry about the negative in this context. And what we see is that Z is equal to the square root at 1 minute, X is 90, and Y is 120. And so I get that Z would be 150. I'll put that 150 on my diagram. So really importantly that at 1 minute, Z is 150, X is 90, and Y is 120. So if we go back to our original equation, which was 2Z times dz over dt, sorry, our derivative, is equal to 2x times dx over dt plus 2y dy over dt, we can now plug in all the information that we know. And the only information we don't know is dz over dt, which is what the question is asking us to calculate. So I'm going to make that substitution. We're going to have 2 times 150 times this unknown dz over dt is equal to 2 times 90 times 1.5 plus 2 times 120 times 2. That 2 is the rate of change that the woman is walking away, or sorry, the rate at which the woman is walking away. And then from here, it's basically using your calculator. I will show that manipulation, and all I'm going to do is divide the right-hand side by the 2 and the 150. And I get, we can do some of this multiplication. So 2 times 1.5 is 3, 3 times 90 is 270, 2 times 2 times 120 is 480, and that's all divided by, and I'll write it in just to make sure we saw where that quantity went, 2 times 50. And if we plug that in and evaluate, we end up with 2.5 meters per second. And it is really important that this dz over dt is not a constant rate. As they get further and further away, we would actually see that change, which doesn't really have a lot of real world application unless you want to talk about 2 people walking away and the distance between them, which is what we just did. All right, that's related rates. Not an easy chapter, not an easy section, I should say. Takes a lot of practice, but fortunately there are kind of that discrete number of questions that we ask, and definitely practice these ones. I do like this distance equation. It does come up a fair amount. And then just to try to be a little more consistent, I am going to put up that assignment. You do have access to the assignment list. Practice makes perfect. You cannot learn calculus by watching videos. You have to learn calculus by doing calculus, which is a bummer, but not really, because calculus is a lot of fun. Okay, till the next video.